Ladies and gentlemen, welcome back to the Big Bear Math Channel. We're cruising towards that AP Calculus exam, and we pulled up a question from 2018. This is question number 3, and if you look below, you'll see a link to this question where you can open up in your own window, and if nothing else, you can keep this graph front and center on part of your screen. This is a non-calculator question. This is an excellent question for any student enrolled in either Calc AB or BC. And let's dive in. Let's jump in. So they've given me a picture of G, and they said G is the derivative of F. So we're thinking, okay, if I've got function F and I derive it, the answer is going to be G. And basically what that's implying is that F of X is the antiderivative of G, if you want to think of it that way. Okay. And let's see, G is totally piecewise until you get to x equals 3, and from 3 to 6, we got ourselves a nice parabola. So part A says, hey, if we knew f of 1 was equal to 3, what's the exact value of f of negative 5? And basically, we want to know how much did function f change from that time period x equals negative 5 until x equals 1, and we can kind of figure out and work backwards, see who f of negative 5 is. In order to get that done, I'm going to use the First Fundamental Theorem. This is a great theorem. College Board is going to hit us on this over and over and over again. And so in a general sense, the First Fundamental Theorem of Calculus says the integral from a to b of, we'll say, f prime of x is guaranteed to be f of b minus f of a. And as a little sidebar, the difference of these two values measures the net change in f over that time period. So drawing, let's see, the specifics out of this question, we're going to integrate from negative 5 to 1. We know by the theorem that's guaranteed to be f of 1 minus f of negative 5. We're basically going to treat this like an equation where we try to isolate this particular term right here. And by doing a little bit of algebra, we could write that f of negative 5 is actually f of 1 minus the value of this definite integral. Okay, now, first things first, we know that this term right here is equivalent to a 3. That was easy. Now, this bar right here is going to be the area, we'll just write area for now, bounded by that G function they gave us and the x-axis. So I got to slide back to that graph, and I got to calculate all those little areas. So looking at your graph that you may have open on your screen, I've got a rectangle that's got an area of negative 9. Now, why did I say negative 9? Well, it's 9, but it's below the x-axis. The next triangle is negative 1.5, or negative 3 halves, and then the next triangle is above the x-axis, and it's positive 1. And so let's see, if I combine all those areas, I get negative 19 halves, or about negative 9.5, I believe, and that's going to make 25 halves. So f of negative 5 is equal to 25 halves. All right, you can take that bear to the bank. All right, for part B, we're going to evaluate another definite integral, real similar in a sense to how we just evaluated the definite integral from negative 5 to 1, but now we're going to go from 1 to 6. And so basically, I'm going to split this into two integrals because we've got piecewise functions up till 3, and then this quadratic function from 3 to 6. And unfortunately, that 3 falls between my bounds. So I'm going to think of it this way. I'm going to do an integral from 1 to 3, where the area is 4. And then I'm going to do an integral from 3 to 6, and then I got to do that by hand basically to find the area of those respective regions right there. So that's how you're going to see me do this. We're going to split this into two integrals. So let's go integral. We got an integral from 1 to 3 of g of x plus the integral from 3 to 6 of g of x. We said that first integral right there, we just calculated the nice square to have an area of 4. And now I need to do this part by hand, and I need to do it algebraically basically. And I'm going to say, okay, we got the integral from 3 to 6. We got 2 quantity x minus 4 squared dx. I am going to do a little u sub on this one just to make sure I cover all my bases. I'm going to let u equal x minus 4, which means du equals dx. And I'm real happy about that because I don't have any extra miscellaneous coefficients to try to keep track of. So let's see, I'll go back to green here for a second. We've got 4 plus. I'm going to take this 2 and slide it out front. I'm going to rewrite everything in terms of u, and this is such a great habit to get into. So that lower bound that used to be a 3, well, subbing a 3 in right here makes -1. Subbing a 6 in right there makes +2, and now this is u squared du. I just replaced the dx with the du because they were equal to each other. Okay, now if I integrate that, the integral or antiderivative of u squared is going to be 1/3 u cubed from -1 to 2. And at this point, there's really, it would almost be a disadvantage to rewrite everything in terms of x. Again, both the function and the bounds. It would be a waste of time. So I'm just going to, since I'm already in terms of u, I'm just going to stay right here. And let's see, 4 plus, I'm going to kind of pull that 1/3 out to make 2/3. Substitute the 2 in for u, and then substitute the -1. And let's see, 9 times 2/3 is going to make 6. 4 plus 6 makes 10. Boom, final answer. Part C says we want to find any open intervals where f is both increasing and f needs to be concave up simultaneously. So let's break this into two thoughts. If you know that f is increasing, what has to be true? You know that f prime is going to be positive. In this case, f prime is the same as g, so we're saying g is positive, and graphically that means we're going to be above the x-axis. So I'm going to make a little note to myself that g needs to be above the x-axis, and that covers the increasing. Now, if f is going to be concave up, the first thing I know is that f double prime is going to be positive, which basically means, now remember, f double prime just happens to be the first derivative of f prime. So in this case, f prime would have to be increasing, or g would have to be increasing. So basically, I'm going to go to that picture, and we're going to try to figure out when is g above the x-axis and increasing all at the same time. And I think that's going to happen. Let's see. We'll say it's true right here. We're above the x-axis and increasing, and then that's true right along here as well. So ultimately for part C, I'm going to say the interval or open interval from 0 to 1 joined or married, unioned with the interval from 4 to 6. Boom, part C is all done. All right, moving right into part D. Find the x-coordinate of each point of inflection for f and give a reason for your answer. Here's the number one thing I want you to write down. Okay, not even worried about the specifics of this question. When you talk about points of inflection, this is one of the biggest mistakes on the exam. What we know is f double prime has to equal 0, or maybe we'll say doesn't exist. Either one's fine. But number one thing is that f double prime must change what? Must change signs. Whoops. All right, and I can't put enough exclamation marks on that bar right there. F double prime has to change signs. So let's go take a look at this picture. And it basically, f double prime, let me write this here first, is equal to g prime, which is going to be the slope of g, the picture we were given. So we're reading slopes. And let's go read some slopes, shall we? And pull out a different color here. Hopefully. All right. So right now my slopes are 0, 0, 0. The slope doesn't exist right there at -2. So I'm thinking, is that a point of inflection? Well, because the slopes go from 0 to positive. That's not considered a sign change. Same thing here at -1. We'd say f double prime doesn't exist at -1 because of that sharpness of the graph. But again, we don't get a sign change. Still don't have a sign change. Okay, at +1 here, the second derivative doesn't exist, but we're going from positive to 0, so that's not considered a sign change either. And at x equals 3, our signs go from 0 to negative. That's not considered a sign change, but watch what happens right here at 4. The slope of g was negative. Now it's positive. We finally got a slope or a sign change at 4. So we're going to say f has a point of inflection at x equals 4 because now you got a couple of different options you could go with here. We could say f double prime change signs. What I'm going to do in this particular case is I'm going to say it's because g that was given to us, because g of x changed from decreasing to increasing. In other words, we're basically saying g prime itself changed from negative to positive, and that gets it done for us. So if you found this helpful, hit the subscribe button below here and continue to follow us. And again, as always, leave some feedback. Help us do a better job of explaining these to you guys. All right. Thanks a lot. Good luck.